Predicting the motion future with Newton's second law often requires us to model appropriately interactions of the system with the surroundings. So, today let's discuss how to model the force exerted by a spring where the spring is in contact with our system. We will have occasion to use this model later for predicting motion in some real-world examples. Let's consider first a spring by itself, hanging from an attachment point. If the spring has negligible mass, then the spring will be at its relaxed length, which we will call L0, where relaxed means the spring is neither compressed nor stretched. When the spring is relaxed, it exerts zero force. Now let's stretch the spring to a new length L that is larger than L0. If, as we show here, the spring is attached to an object, then the spring exerts a force on the object. We'll call that force F1 here. The direction of the spring force is always such as to try to restore the spring to its relaxed length, meaning that if the attached object were to move in the direction of the spring force, the spring's length would change from L to something closer to the relaxed length L0. The magnitude of the spring force is proportional to the magnitude of the stretch, which is the absolute value of the difference between L and L0. Often we give this difference, L minus L0, a special symbol, S. Now the words is proportional to means that there is a constant, which we will call K sub S, such that the magnitude of the spring force is equal to K sub S times the magnitude of the stretch. K sub S, which is also called the spring constant, is a positive number that depends on the properties of the spring. Now, this expression that we have here describing the spring force is known as Hooke's law. Now, if the spring is compressed instead of stretched, then the spring force still tries to act to restore the spring to its relaxed length, meaning the force is again in the direction such that if the object moves in that direction, then the spring is closer to being restored to its relaxed length, L0. Moreover, the magnitude is still given by Hooke's law. Now, we will find it useful to come up with a vector expression for the spring force. So to get started, let's consider this case, and let's first define a vector that gives the direction of the spring force. We define the vector L, which, as shown, specifies the location of the movable end of the spring with respect to the attachment point, which we will take as the origin of our coordinate system. We can use the unit vector L hat to describe the direction of the spring force, since both L hat and the spring force will always be aligned with the axis of the spring. Now, in addition, the quantity S, the difference between the spring's length and the relaxed length, is given by S equals the magnitude of the vector L minus L0. Notice when S is positive, the spring is stretched, and when S is negative, the spring is compressed. Putting this all together, we can describe the spring force F with the vector expression minus K sub S times L hat. Now the magnitude of this force is just Hooke's law. So that's just what we want. Let's check the direction for this case where the spring is stretched, which means S is positive. So the product K sub S times S is also positive. This means the direction of the vector F points in the direction of minus L hat, which is, in fact, the direction that would restore the spring to its relaxed length. So that's right. You can check to see if the spring was compressed instead of stretched, as it is here. The direction of the force would still be toward the bottom of the page, which again would restore the compressed spring to its relaxed length. So that's good too. Now, as a final note, we have here been thinking about the spring as if it were confined to one spatial dimension. However, the vector expression for the spring force we have will also work for spring motion in more than one dimension. Say, if the spring were to swing back and forth as well as from top to bottom. Let's try this question about working with the spring force. Here's the answer. The origin of our coordinate system here is the attachment point. And we choose the positive y direction toward the top of the page. The L vector points from the attachment point to the other end of the spring, so the L vector points also in the plus y direction, and therefore we'll have only one non-zero component, a positive y component. The magnitude of the L vector is just the compressed length of the spring, 0.1 meter. So putting all that together, we find the L vector is correctly expressed as shown.